This really starts the second half of the intermediate algebra course and starts making that progression from intermediate algebra up to those higher level math courses. And we start using the language of higher level mathematics and some of the concepts that go along with it. So this is really the first part. Chapter 8, we call it an introduction to functions and absolute values. And actually, towards the end of the chapter, we will get into complex numbers as well. So what is a function? Why do we have a separate set of language for functions versus just plain old equations? Well, my example was this. Suppose you make $15 an hour at your job. You could write an equation that gives your salary as a number of hours that you worked. Okay, so you could write something like y equals 15x. And if you work 0 hours, you get $0. If you work 1 hour, you get $15 and so forth. And you could work the other way too, where you tell me how much money you made and I tell you how many hours you worked. But you could also represent the salary as a function of the number of hours you worked. And when you deal with functions, you have independent variables and dependent variables. F of x is what we call function notation. We're saying that it's a function of some variable, in this case x. So f of x equals 15x. That's a function that describes how much money I make based on the number of hours I worked. So the independent variable is the one that you choose. The dependent variable, well, depends on what you choose for an independent variable. So you might say, I worked 10 hours this week. Your number of hours is the independent variable because you tell me how many hours you worked. The salary or the output depends on what you tell me. So if you tell me you work 10 hours a week, then I can give you the function evaluated at 10. So 15 times 10 gives you 150. So the independent variable is the number of hours that you worked. The dependent variable is the salary that you earned for that amount of work. Independent, dependent. So why use functions? Well, like I mentioned, that we're heading towards higher level mathematics, and functions are one of those terms that are part of the language of higher level math. But functions also mean something. If you label something a function, that gives you some specific meaning about that equation. And we'll explain a little bit more about that in a minute. It also turns out that it's easier to label functions. If you have 4 different graphs, you might call them y equals for all 4 of them, but that doesn't help me to distinguish one from the other. When you use function notation, you can call them things like f of x, and then you can call the next function g of x, and you can call the next one h of x. So you can label those functions differently, and then you can refer g of x, h of x, f of x, etc., rather than just calling them all y equals. So what is function notation? I mentioned a little bit about it. It's got an f of x, and oftentimes we use f of x for functions, but that's not restrictive. You can use other letters too. Oftentimes you talk about the height of an object over a certain amount of time. Well, in that case, you can refer to the height at a certain time as h of t, right? Where t is the independent variable. You choose how many seconds have gone by since you've kicked the soccer ball or dropped the math book from the roof or whatever, and then the height is given at that time t. So t is the independent variable, height is the dependent variable. So when I introduce functions, I like to think of functions as a function machine. So consider this function f of x equals 2x plus 3. So I have this handy function machine here, 2x plus 3. What does this function machine do? Whatever you put into the function machine, the machine takes whatever you inputted, multiplies it by 2 and adds 3, and then something comes out of that function machine. Right. Now, modern day function machines are programmable, so you don't have to buy a new function machine every time you get a new function. Back in the old days, they were rough. But now, modern technology allows us to change these things on the spot. So what is f of 3? F of 3 means I put a 3 into my function machine. What did we say the function machine does? It takes whatever we input, multiplies it by 3, and then adds 3. So 2 times 3 is 6, plus 3 is 9. So if a 3 goes in, a 9 goes out. Now this function machine just keeps performing the same process over and over and over. Whatever you put in, multiplies it by 2, adds 3. So let's say you put a 0 into the function machine. You certainly can do that. It takes the 0, multiplies it by 2, and adds 3. 2 times 0 is 0, plus 3 is 3. You can put negative numbers into my function machine. Take that negative 1, multiply it by 2, and add 3. So negative 2 plus 3 is equal to 1. So a negative 1 goes in, a positive 1 goes out. All right, what if I gave you this one? What if I said g of x equals x squared plus 5? So here my purple function machine takes the input, squares it, and then adds 5. So let's try g of 3. G of 3 takes the number, squares it, and adds 5. So 3 squared is 9, plus 5 is 14. So if I put a 3 into my function machine, a 14 would come out of the function machine. Let's say I tried that same thing with the 0. Let's try g of 0. G of 0 means I put a 0 into my function machine. What does the rule say? We square the 0 and add 5. So 0 squared is 0 plus 5 is 5. So if a 0 comes in, a 5 comes out. We got to be careful what happens with that negative 1. So g of negative 1 is negative 1 squared plus 5. Again, remembering that the negative's on the inside, the square is on the outside, so we're really multiplying negative 1 times negative 1, which gives us a positive 1. 1 plus 5 equals 6. So we might say that g of negative 1 is equal to 6. If we put a negative 1 into the function machine, a 6 comes out. Now, functions can be a little bit more complicated than that. We have two functions up here. F of x equals negative 3x plus 5, and g of x equals the square root of x minus 2. So I got a whole bunch of questions down here. Find f of 3, find g of 5, and so forth. Let's tackle a couple of these. What is f of 3? For f of 3, we replace the x over here with a 3. So we get negative 3 times 3 plus 5. Negative 3 times 3 is negative 9, plus 5 is negative 4. So f of 3 is negative 4. Right, one next to it says g of 5. Now, you notice we've got two different functions, so having those letters that are different from each other, not just y equals, but f of x, g of x equals, tells me which function I should put that 5 in. So the 5 does not go in the first one. The 5 goes in this one right here. Square root is over the whole thing. 5 minus 2 gives me 3, but that 3 is under the radical. So g of 5 is the square root of 3. What else could we try? How about the third one, f of 2/3? Same idea, except now we have to deal with fractions, but that's all right. We'll get negative 3 times 2/3 plus 5. 3 cancels top and bottom, gives me a negative 2 plus 5, which is 3. So f of 2/3 is just 3. Let's take a look at g of 2 and g of negative 2. If I come down the bottom and find g of 2, now again it tells me which function to use. So if I'm going to use information about g of x is the one on the bottom. So g of 2 is the square root of 2 minus 2. Again, square root over the whole thing, 2 minus 2. Square root of 0, yep, that's fine. Square root of 0 is 0. I'm good. Look at that last one, g of negative 2. G of negative 2 would be the square root of negative 2 minus 2. Again, I'm just replacing those x's with whatever value they give me. Negative 2 minus 2 is negative 4. Square root of negative 4 does not exist in the set of real numbers. It exists in the set of complex numbers, but I'm not there right now. So if I'm just trying to keep it real, then this does not exist. Or we could say it's undefined. Now, the very last question down here is phrased a little bit differently from all the other ones. It says, for what value of x does f of x equal 17? So again, we're up to the top function here, that negative 3x plus 5. So for what value of x does f of x equal 17? So let's replace that f of x with a negative 3x plus 5. So the question is, for what value of x does negative 3x plus 5 equal 17? And then the rest of it is just a little bit of algebra solving, right? Subtract a 5 from both sides, and I get negative 3x equals 12. If I divide both sides by negative 3, x equals negative 4. So you notice that the question didn't say find f of 17. It said for what value of x. So I've answered the question. For the value of x as x equals negative 4, then f of x equals 17. If you put negative 4 back into the x that I have circled up on the top of the slide, negative 3 times negative 4 is 12. 12 plus 5 is 17. It works out. Right? So read the question carefully to see which one you need. Hey, just a couple of things to look at on this slide over here. Notice I got three functions, f of x, g of x, h of x. H of x is the absolute value of x. Whatever number we put in, the answer will come out as a 0 or a number that's greater than 0. So for example, if you look at h of negative 2/3, that would be c over here. This says take the absolute value of negative 2/3. Right? So the absolute value of negative 2/3 is 2/3. Notice for letter h, it says g of x plus h. That's a funky looking one. Can I replace the x plus h, or the x over here with an x plus h? Sure I can. So g of x plus h is going to be that x plus h squared. So when we do these replacements, we replace the variable with whatever we're given. So if we're given a whole expression, in this case x plus h, then we replace the x with an x plus h, and then we carry on from there. So in this case, when we expand it, we're going to have more than just one or two terms. We're going to end up with 3 terms. Let's see how that works. What is x plus h squared? It's a binomial squared. So first term squared. If you look at the insides, you get xh. Double it, you get 2xh. And then the last term, h squared. All right, look at letter D. Letter D says f of negative 2. So which function do I use now? I use this one over here. So I get 2 times negative 2 plus 1. Negative 4 plus 1 is negative 3. One more. Let's look at f of a. F of a is replace the x with whatever is in the independent variable spot, which in this case, I'm just replacing an x with an a. So I get 2a plus 1. Right, a little bit more practice. This one says evaluate each function f at the given value of x. And so really I just put this in here. It's the same stuff we've done already. I just put this in here because I took the wording from the textbook. So you're going to want to be familiar with that language when you go to solve the problem so that you know what it is they're looking for. So when it says evaluate at the given value of x, here's the given value of x. So let's try that. In other words, for number 2, I want f of 2. F of 2 is 2 over 1 minus 2. Okay, order of operations, let's simplify the bottom first. 1 minus 2 is negative 1, and then 2 divided by negative 1 is negative 2. So I've evaluated at the given value of x. The given value of x was 2, so wherever I saw an x, I replaced it with the 2. So what are different ways that we can represent a function? We can represent a function verbally. We could say in words, every x is multiplied by 15, right? Let's go back to my example of earning $15 an hour. I can explain it that way. I can make a table of values. I could make a table where 0 gives me 0, and 1 gives me 15, and 2 gives me 30, and 3 gives me 45, and so forth. And I could look at that table and realize that the second column is always 15 times the first column. I could represent it with a formula. Right? Remember the formula we had before when we were figuring out the salary? F of x equals 15x. So there it is with a symbolic representation. I can make a graphical representation. I could graph on the xy plane and start at 0, 0, and go over 15 and up 1, over 15 and up 1, and so forth. And I would have a graph that gives me the y value for every x value. And then the last one is what they call a diagrammatic representation. In other words, we're going to draw a diagram, and we'll see in a minute that all we're doing is matching up items in the domain, or the independent variables, with items in the range, which is the dependent variable. So here's an example of sweatshirts. You're going to order sweatshirts for your baseball team. There's a sale where you can buy a maximum of 20 sweatshirts at a price of $30 each. So express this verbally, I kind of just did. I can buy 30 times the number, I'm going to spend 30 times the number of sweatshirts that I buy, up to a maximum of 20. So the independent variable is the number of sweatshirts. In other words, if you want to find out the cost for this company, then you're going to have to I'm going to have to tell you how many sweatshirts, and then the dependent variable in this case is a y, or the cost. So it says express as a table of values using 5 values for x. So I've got x and I've got y. Remember, x is the number of sweatshirts, y is the cost of buying those sweatshirts. So if I buy one sweatshirt, it's going to cost me $30. If I buy 5 sweatshirts, 5 times 30 is 150. 10 times 30 is 300. Let's do 16. Right? 16 times 30 is $480. It says up to a maximum of 20. So if I buy 20 sweatshirts, it's going to cost me $600. So the question just said to pick 5 values for x. I picked 5 values for x because that's the independent variable. I made sure my answers made sense. I didn't pick fractions of sweatshirts. I didn't pick negative sweatshirts. And I didn't pick any sweatshirts above 20 because it says that's the maximum number I can buy. All right, so we did that with a table. Evaluate it symbolically. F of x equals 30x for x values between 0 and 20. Express this graphically. Well, not exactly a perfect graph here, but if we were to make one, number of sweatshirts would go over here, and then the cost would go over here. So one sweatshirt would cost me $30, 2 sweatshirts would cost me $60, and of course no sweatshirts cost me $0, and I can go up from there. All right, express using a diagram. A diagram is a mapping between 2 sets. So here is an example of a mapping diagram. Set A is the number of sweatshirts, and set B is the cost. Now, there's no meaning to the way these things are drawn in terms of, well, one of them has an oval and the other one looks more like almost a rectangle, but not quite. No, it's just we're going to make a picture of a set, so we're just going to make a picture of a set. It doesn't really matter how it's set up. And you notice that it's a mapping from one column to the other. And so 0 sweatshirts cost me $0. 4 sweatshirts cost me $120. 12 sweatshirts cost me $360, and so forth. Obviously, there's a lot of numbers in between that are missing, but that's the basic of a mapping diagram. So now we get into the definition of a function. Remember I had said before that a function has a special meaning. If I say something is a function, that means something more than just saying y equals something. And so a function is a set of ordered pairs where each x value corresponds to exactly one y value. Functions have both a domain and a range. The domain is a set of all x values. The range is a set of all y values. And so when we go to find information about this, we're going to want to know what is the domain and what is the range. What numbers can I input? What values are allowed to be output? So in the case of the sweatshirts, the number of sweatshirts is the domain. The range is the cost. Now, I said a set of ordered pairs is called a relation. A function is a special type of relation. So any pair of x, y coordinates that form any kind of relationship, I mean, you could be tracking the number of miles you drove and how long it took you to get there. That may not be a function, but it is certainly a relation. So what sets a function apart from anything else is that each x value corresponds to only one y value. In other words, the x values don't repeat. So if you were tracking number of gallons of gas that you bought and how much it cost for a fill-up, the cost for the fill-up should be the cost of a gallon of gas times the number of gallons. If 2 people went to the gas station and both bought 17 gallons of gas, but it cost them different amounts of money, then now each x value has more than one y value. So if I went there and filled up for 17 gallons and it cost me $55, and you went paid for 17 gallons and it cost you $60, then we don't have a function anymore because we both put in the same X value, but we got different Y values, which means we paid different amounts for our gas. All right, so it says make a table and graph the following. Determine domain and range for numbers 1 through 3. And then for 4, 5, and 6, just give domain and range. So I'm going to separate this, and we're going to do another video where we do just these last couple of examples. And we'll look at domain and range and figure out what makes sense.